The course is Solid State Physics, and this lecture is about 3.2.1 macroscopic picture, and we will be focusing now on the elastic deformation of solids. So what we will do first is that I will just introduce to you the elastic constants that we use to understand mechanical properties of solids. So mainly we will introduce to you Young's modulus, shear modulus, bulk modulus, and Poisson's ratio. So essentially that's a relation that connects, relates, transfers, and longitudinal strain together. And then we will find out the properties, these macroscopic properties are somewhat related to each other, giving us useful rules of thumb. So these are the elastic constants that we referred to in the earlier lectures. And then in the second lecture, I will go into the elastic deformation and the microscopic description. But first, I will go through the bits and pieces of terminology and focus on the macroscopic picture. So elastic constants. These are material properties that we can define when the material is still in the regime of elastic deformation. And this regime is actually very narrow. So what we see in the picture is highly exaggerated. So it's actually quite narrow, so that the strain that the material will be amount of strain that the material will be deforming is not much. So we're speaking a few percent when we are still in the elastic deformation regime. So please be noted and warned that this actually should be very steep. This curve we would be seeing here. But I felt that doesn't make a nice, good picture conceptually. So that's why I wanted to broaden up the regime of elastic deformation. And when we are looking into other fields, not into physics, for example, in material science, when we are looking at the real materials and we want to improve their properties, this is also often the region of most interest. So that this is many times where we want that the material is being used, so that it's not being permanently deformed, but rather can be used in a continuous basis. So, for example, like an example from a family with small kids in the house, those Lego bricks that we may or may not have as children's toys, the deformations that we take use of them so that we can actually stick Lego bricks together like they are naturally elastic deformations, so that we can keep on happily building Lego buildings and ships and whatnot, and we can tear the structures apart and we can build again, and we can repeat this cycle thousands of times, tens of thousands of times with these Lego bricks, and still they remain in their original shape, so that we know that there are some elastic deformations taking place that then enable us to put them together, but they are not strong enough so that they will actually be plastically deformed. And that being said, this doesn't mean that the solids should not undergo plastic deformation. It's just a matter of application, that what is your interest. And sometimes we even intentionally, few words on this later, we even sometimes we try to improve the properties by intentionally going beyond the elastic deformation regime for a while, so that we can then increase and change the properties of the material by just doing some work hardening, and that could, for example, be used to improve the properties a little bit. But more of this process later. And in this regime, looking at the curve, we have a linear relation between the stress and strain. And because of this fact, we can actually introduce material parameters, and these parameters are known as elastic constants that then describe the responses. So this is the nice thing about linearity in the system. So then we can just really have a single constant, and then with them we can understand when we apply a given amount of stress, we know how much the material is being strained. So this is the brief outline to elastic deformations. And now to the actual topic. So to 3.2.1, the macroscopic picture of solids that are being elastically deformed. Let's start by defining an elastic constant known as Young's modulus. And essentially, what we do here is that we define Young's modulus via a relation that we have a ratio of stress and strain, and this ratio is defined as the Young's modulus. And mathematically speaking, I'm saying here that Young's modulus y is defined as the ratio of sigma to epsilon, so stress to strain. And plugging in the equations, what we have discovered for stress and strain, we realize that this is equal to F divided by A. F is the applied force, A is the cross-sectional area perpendicular to the force, and then we have the inverse of the relative length change of the material, so the inverse of strain. And Young's modulus can be interpreted basically as the slope of the stress-strain curve when we are in the elastic deformation regime. So this is the mathematical interpretation we can have, and this also works physically. Okay, what's next? Another elastic constant is known as a shear modulus or modulus of rigidity, and this is quite similar to Young's modulus y, and it's either called modulus of rigidity. The symbol is always G, and it's also known as shear modulus, and I think I prefer myself shear modulus. It's easier to pronounce, and then somehow I prefer the fact that we have this word shear in the terminology here, because we are actually applying a shearing stress for the material, and the material will shear, so somehow shear modulus is a very illustrative term to me. And this is defined, this shear modulus G, as a tau, which is the shear stress, divided by alpha, which is the deformation angle. And somebody might be wondering that why don't we have a sine of alpha or cosine or tangent there, we just have the angle. And this is due to the fact that usually we have very small angles in question, so that the materials don't really shear that much when we are applying a shearing stress into them, so that we can really speak of a few degrees or a lot less in terms of the deformation angle, and then we do not need to care is it a sine of alpha or just the alpha. So this is what happens graphically. We are applying a force, and now it's parallel to the area A, and then the solid is being deformed, and the deformation angle is there denoted in the picture with alpha sign symbol. And shear modulus Xi essentially describes the material's inclination to shear, how easily it will be shearing. Then yet another elastic constant, bulk modulus. And in the possible case that the applied stress is uniform, so we mean now that all the sides of the solid are under the same kind of stress. So for example, hydrostatic pressure is an example of this. Then the volume V of the solid is being deformed. And this is characterized by bulk modulus K. And the bulk modulus K is defined that it's the minus of V, the original volume of the solid, times the derivative of pressure with respect to volume. So this is the definition. It seems obscure, but this is the way to do it, so that we can actually use it nicely to describe the change of volume with respect to compressive force. And the sign convention has been used such a way that when we have a positive K, then we will have a compressive force, and that will compress the solid. And the picture there shows what is happening here when we are speaking of bulk modulus and compressive, hydrostatic pressure. So we are pressing with the force, equal force from all sides, and then this force will deform the solid. And the kind of scenarios I can imagine first comes to mind is something submerged underwater. For example, what about like a submarine? Or another case could be that what about like a hot air balloon or something like that floating in air, and then the pressure of the atmosphere that is affecting the properties of that piece of a solid. So these are the kind of some example scenarios I could come up with when we are dealing with these kind of forces. And another one might be, I'm not sure if this is actually relevant, but at least when we are shooting a satellite and we are like building the satellite on Earth in a normal atmospheric pressure, and then if we successfully get the satellite up into the space, there won't be any more atmospheric pressure that the object is facing. That might affect the mechanical properties of that solid, so should be taken into consideration. But probably this is not very, very major thing when one is realizing satellites. But at least in principle, it's something that should be at least considered. Maybe it's not relevant, but at least acknowledged that it might be relevant. So, like I said, sign convention is chosen such a way that when we have a positive bulk modulus and when we have a compressive force, then the solid will compress. And this is a good sensical rule, I would say, that we have a positive valued elastic constant, and this corresponds to a compression when we have a compressive force. So this is the reason why we have put in the minus sign there. So we have now covered the basic elastic constants. So bulk modulus, then the shear modulus, and then the Young's modulus. And we will next start looking into the kind of interrelations of these properties, because we will be then utilizing later this interrelation in order to estimate things, and then that's the kind of like a 1-1 motivation here. Another motivation for the what follows next is that these will also ease up some of the calculations and provide more physical intuition to the system at hand. So there are good things to cover. So let's cover next Poisson's ratio, and I will start by the introduction by just making a Gedanken experiment, a thought experiment, and we assume that we have an incompressible solid, and we assume that the volume is V, and when we stress the material, the change in the volume will be 0. So that's the definition. That's what incompressible solid or liquid means. That the volume is not being changed when we apply forces into it. And this is usually a very good assumption to make when we are dealing with solids and liquids, that they are incompressible objects. Stress, we assume that they will be applied in one direction, and then it will compress the solid in that direction. And then what will happen is that then the other directions need to expand, or vice versa, as in the picture. So we apply a tensile stress, and this will elongate the solid, and then these other directions, they will need to be getting shorter. And this effect that seems very intuitive, we quantify how strong it is via Poisson's ratio nu. And we define Poisson's ratio as the axial strain along the index 2 direction. So please, the index 2 there corresponds to one of those transverse directions, so perpendicular to the applied force. And this is equal because we're assuming that we have an isotropic material. This is equal to the other transverse strain, and then this is equal to minus this Poisson ratio nu times the axial strain. So now we have the index 1. Sorry. And this is, of course, we can just rewrite that the by definition that the delta L1 divided by L1, that's the strain 1, so axial strain. So this is Poisson's ratio, and physically it tries to answer this question. Okay, like if we deform a solid by deforming it, we like are applying a tensile stress into the solid, and then we know that this direction of the solid will elongate, and then these other directions they must get narrower, they must reduce in dimensions, and Poisson's ratio is telling to us exactly this. How strongly the material changes. So we found the Poisson's ratio to be of this type of an equation. And please note here that we are really assuming a isotropic material. And this implies to us, forces to us that the transverse strain epsilon 2 must be equal to the other transverse strain, so epsilon 3. And now the Poisson's ratio nu is, in other words, the negative of the ratio of the transverse strain, so either epsilon 2 or epsilon 3, with respect to the axial strain epsilon 1. So essentially, like what Poisson's ratio can be also written to be is that we had the earlier equation here, and this is essentially the definition of the transverse strain epsilon 2, and this is the definition of the transverse strain epsilon 3, and this is the definition of epsilon 1. So we can really rewrite the Poisson's ratio that the epsilon 2 equals epsilon 3, and this must be equal to Poisson's ratio times epsilon 1. So essentially Poisson's ratio is the minus of ratio epsilon 2 divided by epsilon 1. So transverse strain with respect to axial strain. Okay, let's now look into the mathematical properties of Poisson's ratio, and we will show next that it's actually a bounded parameter, and it's bounded into a range where it can get values of from minus unity to positive 0.0 values, and we will show this next. So let's consider a cubic solid, and we just assume that it has a volume V, and it's a cubic, and it has the length dimensions L1, L2, L3, and we apply an axial stress sigma 1, and this deforms the volume into something, different volume. And with V prime, we now describe the deformed volume after an axial stress has been applied into our piece of a solid. And now we know that the lengths will get modified. So we have the original length L1 plus its change times the length of the original along the second direction times the relative change of this direction, and then the third one. And this is now giving us the new volume V prime of our solid. So what we have, we can multiply all of these terms together. We just multiply L1 with L2 and L3. We have the first term, and then we have the other terms, like we have L1 times L2 times delta L3, and then similarly we have L1 times delta L2 times L3, and then these other terms that we have in there. So essentially we go through and we multiply them, and the final one, we multiply this guy, this guy with this guy, and this guy, and this is how we land with this. And we just multiply this out, nothing strange here. So we have lots of different looking terms. I do not try to do this tongue twister myself. I would just like to show that these are the terms. You can verify yourself that this is indeed what happens when we just perform the multiplication of the three terms in the parentheses. And we know that the strain is actually quite small, so that the relative change delta Li is a lot smaller in value than all of the Lj's. And this is okay for any I and any J. And this allows us to neglect these higher order terms basically the ones which we have 2 delta LIs in here. So we can neglect, for example, this term, and this term, and this term. So these are the higher order terms. And this is okay to make this approximation as long as this condition is okay for any I and j. So essentially this means that it's a pretty cubic-like object and not a very rod-like strongly elongated object. So now we have an equation for the deformed volume V prime, and we can approximate that this is then of the form that we have V prime, and we have the original volume L1 times L2 times L3 plus the first order contributions to the change of the volume. So delta L1 times L2 times L3 and these other terms. Looks nice, and this is very logical so far. And we will continue and see that this is also very logical all the way down to the final solution. So now we can rewrite that the first term, this is the original volume V of the cubic object. And because V prime, we can always write that is of the form that we have the original volume V plus some change in the volume. And recalling that we do have this Poisson's ratio that we can take use of. Like we have this delta L2 divided by L2 terms. And we can now take use of this equation for the Poisson's ratio to the above equation so that we can simplify it. So essentially we have the delta V term, so that these terms that we are now looking into, and we are taking use of this equation to rewrite these terms slightly differently so that we can actually write this change in the volume of the object using Poisson's ratio nu. So first term, we do not do anything for that. It's already of the right form. And then we replace on the second term, instead of delta L2, we rewrite it using the equation for the Poisson's ratio. And we find out that it's what we put inside parentheses is minus nu times delta L1 divided by L1. And then we multiply with the L2 and L3. And then the third term, what we have is that we have L1 times L2, and then we replace delta L3 with what we can find out from the Poisson's ratio. So we replace it with minus nu times delta L1 divided by L1 times L3. And now we have lots of similar terms, so that we can rewrite this equation to be 1 minus 2 times nu times delta 1 times L2 times L3. And looking at this equation, we see that, okay, the upper limit, which is nu equals 0.5, like we end up with a situation that the change in volumes is 0. And this is what essentially an ideal incompressible solid is, how it behaves. So that the volume does not get changed when we apply a stress on a piece of an incompressible solid. And this Poisson's ratio gives us this ratio there. Some practical examples out of materials. Rubber is a pretty good example of an incompressible solid. It has a Poisson's ratio close to 0.0. Cork is another one, and it has a Poisson ratio of close to 0. And of course, there's the possibility that we would have -1. So in principle, then the object will behave quite differently to other materials, kind of normal materials. But that may be the case. I don't remember now what are examples of such materials that we have a negative of Poisson's ratio, but I think we do have. I just do not remember what they were, what kind of materials they were, but I think there are such materials. And then we will go in the final slide, go through further relations between the elastic constants we have now introduced to you. We have seen that we can derive the elastic constants from a few fundamental elastic properties. And subsequently, what we can do is that we can also find relations that link these properties together. And for example, Young's modulus Y, shear modulus G, and Poisson's ratio nu, they can be related. We do not show the derivation here, but it's relatively doable. So that G equals y divided by 2 times 1 plus nu, the Poisson's ratio. So this kind of relation we can find between these different elastic constants. And this is quite nice because it provides us some kind of rules of thumb that we can use if you want to understand the mechanical properties of different solids, especially if you know what is, for example, the Young's modulus and Poisson's ratio. Then we can estimate what is the shear modulus and vice versa. Another relation or approximation that we can find, we do not show the derivation here, but it's also doable. The bulk modulus K, the Young's modulus Y, and the Poisson's ratio nu, they are also approximately related via a relation that we have nu, approximately 1/2 minus Young's modulus Y divided by 2 times K, the bulk modulus. And this is known as the Lame's equation, and that can also sometimes be used to estimate the other elastic properties, other elastic constants of materials when we know some of the others. So these are sometimes quite useful equations when we want to estimate things and when we are missing some information that we might seem to be needing. So what we see here, and this will be useful in the upcoming lectures when we are trying to understand plastic deformations, that these elastic constants for a given material, they should really have the same order of magnitude in strength. And this is a very useful rule of thumb because, for example, when we are thinking of a yield stress and yield strain values, like we will in the following, we will estimate like what is the yield shear stress value of a material. And because we estimate then based on these equations that they should be roughly of the same order of magnitude, the yield stress and the yield shear stress, then we can try to approximate and understand things based on a simpler approach. So this is the motivation we will be using slightly later, and that's the part of the reason why we introduced these interrelations between the elastic constants. So I thank you for your time, and this is the end of the first part of elastic deformation, and in the next part we will go into the microscopic description of what happens when the material is under elastic deformations. Okay, thank you, and bye-bye.